All right, hi everybody. Because I've missed a couple days, and so I want to be able to do this. So we're gonna get to Ampere's law, which is here, and we'll also do Ampere's law for a solenoid. So I'll show you what that looks like in a bit. So if you remember, we did Gauss's law, right? That's that an electric flux is equal to the total charge inside divided by a constant epsilon naught. It's called the permittivity of free space, and essentially that is how quickly an electric field will move through empty space. That constant is equal to 8.85 times 10 to the negative 12 coulombs squared over Newton's meter squared. And then I asked you, using Gauss's law and the fact that the flux is equal to the integral of the electric field dotted with dA. And again, the idea is that you have this enclosed shape. So the enclosed shape that we used for a point charge is a sphere, right? And using that sphere, you then calculate the electric field for a point charge, right? Again, one of the reasons we use a sphere is because the electric field is constant throughout, right? Throughout that shape. Okay, so there's that, and you get this. And people might see, yeah, we called it QQ. It's not Q times Q, it's Q subscript Q. So it's the charge inside divided by how far away you are from the point charge squared. And then this is a constant. Well, what does this constant end up being? Because again, people who took physics last year, you're like, oh, wait, I don't remember this. Well, wait, no. If you plug in everything, 1 over 4 pi times that epsilon naught value, you'll get 9 times 10 to the 9 Newton meter squared over Coulomb squared. And yes, that's that K constant that we had before. I think we called it K subscript E. That's Coulomb's constant. So yeah, generally in higher level physics, we tend to write it like this because as we're going to see soon, that epsilon naught has meaning. Okay, so there's that, and I'm not going to solve it though because that's part of your homework, and I think people said they were able to do that. Okay, now we're getting to again. I'm assuming you've taken physics before, so basically we know that a current will generate a magnetic field, right? That if you got a current, if you got a moving charge, the moving charge will generate a magnetic field. So we got that qualitatively, and back in the day, I derived for you, or I kind of gave to you what the actual equation is for a magnetic field of a wire due to a current carrying wire. Well, now we're going to be able to derive that from scratch using something called Ampere's law. Ampere's law is analogous to Gauss's law. The only difference here is that instead of a closed shape, you're doing a closed loop. So what we're going to do is you've got a current moving to the right, and it generates a magnetic field, let's say, at this point. So at this point up here, right, it's going to generate a magnetic field pointing kind of like towards us. Right, I'm kind of cheating a little bit here. So and yeah, so you're going to make up a closed loop, a closed path. Often it is a loop, it's like a circle, but it could be a square, a rectangle, or a star. It could be whatever. Again, you tend to choose shapes, loops, or whatever, paths, if you will, where the magnetic field is constant, because that's going to end up making it so that the integral is going to be much easier to do. So we'll start off with a wire. Wires tend to be cylindrical in shape, so we're going to make a circle around here like that. So again, this DL is just a little bit of path length, DL. So there, right? Yeah, and the magnetic field, as we know from last year, loops around in that same path. Again, you can use that right-hand rule. Your thumb's the direction of the current, finger's the direction of the magnetic field, and you can find the direction of the magnetic field. You'll see that it does that. Okay, so what does Ampere's law say? Ampere's law says this, that basically the closed loop magnetic field dotted with the length, so this is B dot DL, again, another way you could write that is B dl cosine theta, because it's a dot product, so it's dotted with that. This is an integral. If you notice, there's this fancy little circle in here. All that means is that this is a closed loop, that this path that we're integrating around is closed. So often that's used to suggest that it's closed. Doesn't need to be there. It's kind of just sort of useful notation. And it turns out that that's equal to a constant multiplied by the total current inside. So Q in. So if you notice, right, it looks a lot like Gauss's law, right? Because Gauss's law says the same thing. The flux inside, which is the integral of the electric field dotted with the area, is equal to the total charge inside divided by this constant epsilon naught. Again, epsilon naught is called the permittivity of free space. It's how easily a magnetic field will move through empty space. So what about this one? This mu naught? Well, it's not a coefficient of friction, sorry. It's called the permeability of free space. Let's see if I can spell it correctly. Permeability? You tell me later on if I spelled that right. I don't think I did, but yeah. Permeability of free space. And again, what that basically means is it's how easily a magnetic field will move through empty space. That value for a vacuum is equal to 4 pi times 10 to the negative 7 Tesla meters over amps. Yeah, and then, right, current measured in amps. This is the magnetic field, dl. And again, the goal is often to choose shapes where the magnetic field will be constant, so you can pull that constant out of the integral and make it an easy integral for you. Okay. So with that, I'm going to kind of set you up here. So yeah. Oh, so the magnetic field is constant, so you could pull it out, and basically you're going to do that. So what you're going to do is, using Ampere's law, you're going to find the magnetic field B of a wire using just the constants mu, the current I, and then the distance from from where you're measuring the magnetic field from the original wire. So and that's basically this R, the distance R. So that's the distance from the wire to where you're finding the magnetic field. So basically, find B for a wire. You're solving for that, and then again. So that's your next step right there. But I'm going to also go and assign also the solenoid, so I'll explain that one as well. Again, as you can see here, it's kind of a hop, skip, and a jump. So yeah, go ahead and do that. All right. With that then, and if you recall from last year, you kind of should have the equation or have an idea of what the equation should look like. Okay. Next up is a solenoid. Again, we've seen a solenoid. Right, the magnetic field, something that's kind of nice about a solenoid is that the magnetic field inside the solenoid is fairly uniform. It's pretty constant. And then the magnetic field goes out of the solenoid, loops around, and comes back in, and you just have this constant loop going on here. And as we saw last year, this is very similar to a north pole of a bar magnet, because the magnetic field is coming out. And this is like the south pole of a bar magnet, because the magnetic field is coming in. So again, I'm going to set you up with the loop in this case. I'm not going to have you make the loop because this one's a little bit trickier. But typically what we can do, the loop we're going to make is this one right here. I made a little square. It could be a rectangle. It doesn't have to be a square. But we're going to say that everything in the square has a length L. And so it goes down, it goes into the solenoid, out of the solenoid, and back out. Yes, and then we got this closed loop. I've purposely made it go, in this case, clockwise. It could go counterclockwise. It doesn't have to go clockwise, but it could go counter. Yeah, but that's the way I did it. And again, we're going to assume that inside of the solenoid, like I just said, the magnetic field is constant, right? So we're going to use that to the case. We're also going to assume, do I have that here? Oh, yeah. So again, here's Ampere's law. So Ampere's law right here. And again, the idea is that you want the magnetic field to be constant such that you get to pull out the magnetic field out of there. This one's a little bit trickier, though. You got think about what you have here. We're also going to assume that the magnetic field inside is much, much bigger than the magnetic field outside of the solenoid. So the magnetic field in here is much, much bigger than the magnetic field out here. The magnetic field outside is fairly weak. Okay, so with that, the other thing you're probably going to need, or it's going to help you, is that the current inside will be the number of loops multiplied by the current through the wire. So if you think about it, right, the number of loops, these are the loops here. So if you think about like, if I had like a wire here with a current, I don't know, let's say it's got 2 amps going out of the page here at you. But then, and then I grab another wire like this coming out here. This is also going at 2 amps. And I do another wire. This one's also going at 2 amps. Well, the total current going through this box that I just made is going to be 6 amps, right? So basically, the current inside, one way you can write it is the number of loops multiplied by the current through one wire. We tend to write that in physics. Number of loops tends to be capital N. And then the current through the wire is just going to be called I. So that's going to be your I inside. That's my first hint to you. And so, yes, what you're going to do then is find the magnetic field for a solenoid in terms of the length of the solenoid, L. That's a constant. So this is the current going through, capital I. And then this is N, the number of loops. So you're going to find B for a solenoid in terms of all this, but starting with Ampere's law. So yeah, those are the 2 derivations you're going to do. You're going to do first for a current carrying wire. That should be a hop, skip, and a jump for you. This one then is for a solenoid. See if you can figure that one out. Another hint I might give you is break it up into 4 parts. Break it up into the 4 parts of the square, and you'll see you can kind of do each part and then add it all up. All right, so hopefully that helps. And then we got one more of these equations or laws, actually 1.5. We'll talk about it. And then we'll get into relativity. So there you go. All right, hope that helped. And let me know if you got questions. Bye.